It only captures what's on my screen, but it's obviously projected there. Anyway. All right. If you don't have any questions or comments, I guess we can get started. Let me know if you do have any concerns. All right. So, well, let's just begin with a few terminology with differential equations. The first thing I want to kind of talk about briefly is the difference between ordinary differential equations and partial differential equations, because you're going to hear the term a lot in the future. So, ordinary differential equations, sometimes we just write ODE, which is differential equations that has only one independent variable. And for example, if I write dy dx plus y equals 5 as the example, so in this differential equation, the y is depending on x based on dy dx. So that tells you that the y is the dependent variable. And the x is the independent variable. We only have one independent variable in this equation, which is the x. So that's why we call it ordinary differential equations. So this is the x is independent. Now, another example would be, let's just see, well, let me write down first. It's partial differential equations. This is what we call PDE. It has more than one independent variable. For example, if I write this curly d, it's kind of like a 2, but it's a d. It's curly d of y divided by dt is equal to d squared y dx squared. So this is also a differential equation because this really is just like a dy dt, but it's a partial derivative. This is the d squared y dx squared. The reason we use this curly d instead of the normal d is because the y in this case depends on both x and also t. So the x here and the t, they are the independent variables. Both of them are independent variables here. So x and the t are independent. Here we have two of them, so it's a partial differential equation, not an ordinary differential equation. In the future, you're probably going to see more complicated PDEs. You might have something simple like a dy dt, but then it might be dy dx times y, could be d squared y dx dt, and so on. So all of those terms indicating that the y depends on t and also depends on x, right? That's two independent variables. So it's a partial differential equation. And for partial differential equations, we always use this like a curly d instead of a normal d. Don't have to worry too much about it now because we're not going to talk about it until later. The next term is for the order of differential equations. So the order is really just the largest derivative in the equation. for example, the one I had earlier, dy dx plus y equals 5. So you look at what is the largest derivative, which is the first derivative, right? The dy dx. So this part is the first derivative. It's the biggest derivative we have. So this equation is called first order differential equation. So it's just a first order equation because of the biggest derivative. One way I usually try to remember is that if you think about polynomial functions, what's the degree of a polynomial function? You look at the highest exponent of the x term, right? So that's a degree. So here it's saying you kind of just look for the highest derivative. And if I write, let's just see y, the third derivative of y minus 2y second derivative plus y equals 5, I don't know, just y prime, well, doesn't matter now. If you have something like this, if you want to know the order, this is the first derivative, this is no derivative, this is the second derivative, this is the third one, so that's the biggest. So this is the third order. Differential equation. It's just because this is the highest derivative. If we don't have this term, let's say the first term is not there. We just begin with this part, so that will be a second order differential equation. Questions? All right. Another term is linearity. So linear differential equations has no product of dependent, so that's a key there, dependent variables or derivatives of dependent variables. Or square root exponential trig with dependent variables in them. I'll give you some examples in a minute. So what I meant is that so for a differential equation to be linear equation, you cannot have something like, for example, y prime equal minus y squared equals 5. You can't have. So the y here is the dependent variable because you can think about this as the dy dx or dy dt. So y is not independent, dependent. So y is the dependent variable. This is the y squared, so that's a problem. That's not a linear term. It's a quadratic term of the dependent variable, so that is the equation nonlinear. So this is not linear. Therefore, the equation is a nonlinear equation. Sometimes you might have something like y prime squared, or even y prime times y double prime. For example, this is linear because it's just first power of y. But the problem is that you get two derivatives to multiply. So that's not good. That's not a linear term. So that makes the equation nonlinear. Now, what if we have, let's see, y double prime plus y prime minus y plus, let's just say, e raised to the y in exponent equals 5. That's also not good because this is not a linear term. Think about y as a function of x, for example. This is the e raised to a function of x, right? So that's not a linear term, that's an exponential term. So that's not good. So this is also nonlinear. That's what I meant. You cannot have products of the y. You cannot have products of the derivatives of y. You cannot have like a square root of y or e to a y. That will make it nonlinear. Now, what makes it linear? A linear differential equation is something like this. When you have just y prime, the derivative of y by itself, there's no power of this or product itself. Or maybe you have a constant, that's okay too. Or you have this one, is the second derivative multiplied by constant, but the second derivative doesn't have a power, it's a linear term. The y shows up by itself to the first power, first derivative also to the first power. So that's a linear differential equation. Because every term with the dependent variable y in there, it's a linear. Every term there is linear. Questions? You're going to see those again. Now, what about this one? Let's just say y is a function of x, right? So suppose let's just see, what about this? Let's see, x squared y prime plus x cubed y second derivative minus 3y equals 5x squared, for example. Do you think this is a linear differential equation or nonlinear? Linear, right? So this is also an example of a linear because we only look at the dependent variable, which is y. X is independent, so you don't have to worry about it when you look at linearity. So this is a y prime by itself. There's nothing multiplied by another y or derivative. Don't worry about the x, we have the constant. The second derivative, again, there's a power 1 there. This y has a power 1, this x, don't even worry about it. So that's a linear differential equation. What's the order of that equation? 2. Second order, right? So this is a second order because of this part. Tell you it's a second order. And obviously this is a ODE because there's only one independent variable, which is x. You can tell by looking at the derivative. This should be dy dx. This one should be d squared y dx squared. You only have one independent variable. Any questions on those? No? All right. Well, if you don't have questions, we can look at a few practice problems. The first one I have, so is y of x equals c, some constant c, x to the negative 3/2, a solution to differential equation 4x squared y double prime plus 12xy prime plus 3y equals 0, assuming that x is positive. So here we have a differential equation, and if you quickly look at it, it's a second order, and it's linear, and it's an ordinary differential equation. Is that a solution to this equation? What do we do to show whether that's a solution? we plug in, right? We take whatever is given, and then we plug into the equation, see if we maintain the equality. So before we plug in, on the side, maybe we can do a little bit extra work because we need to know the second derivative, we need to know the first derivative. So let's find them on the side. So the y prime is equal to, just take the derivative, right, using the power law, the power rule. The constant c stays. X to the negative 3/2 becomes x to the negative 3/2 minus 1. But then we have to bring the exponent to the front, negative 3/2. Well, we should have done that first. So bring the exponent to the front, minus 1. So that's x to the negative 5/2. I'm going to erase it. And then write x to the negative 5/2. Is that okay? And then now we find the second derivative. Take the derivative again, so that whatever is there as constant stays. So negative 3/2 c stays, but then we bring the exponent to the front, we get negative 5/2, x to the negative 5/2 minus 1. Right, we have to, so we bring the exponent to the front again, we have to minus the 1 from the exponent. I'm going to do it a little bit hopefully. Okay, so that's a negative 7/2. This is x to the negative 7/2 in the exponent. So now we have the first derivative, we have second derivative, we also have the y we can put into the equation. And try to see if we still have left side equals to the right side. So plug in, so we get 4x squared. Second derivative, which is this term. Is it okay if I multiply those two together when I plug in? So that's a negative, negative is positive, and I have 15 over 4c. So 15 over 4c, x to the negative 7/2, that's the second derivative. And then plus 12x multiplied by the first derivative, I'm just going to plug in directly, negative 3/2 c x to the negative 5/2. And then plus 3y, which is 3 times c times x to the negative 3/2. The question is this going to equal to 0? Personally, I don't like to use just equal sign, because if you put equal sign there directly, it means actually equals, right? But you want to show they are equal, so I always put a question mark above it to show that we need to confirm that. And to simplify this, the 4 cancels with that 4, the 2 goes into the 12 6 times, and if we simplify, we get 15c, and x squared times x to the negative 7/2, so that's the x squared times x to the negative 7/2. If you combine those two, it ends up to be x to the negative 3/2. The next term we have minus 18x to the first power times x to the negative 5/2. Again, that becomes x to the negative 3/2 again, if you add the two exponents. And a 3, oh, I forgot a c there. That's a negative 18c times 3c, x to the negative 3/2. And it turns out that we have 15c x to the negative 3/2 minus 18c x to the negative 3/2 plus 3c x to the negative 3/2 equals 0. And you can kind of just combine, either factor out the common factors or just look at it. You have 15 minus 18 plus a 3 multiplied by c x to the negative 3/2. And that should equal to 0 on the left, which is the same on the right. 0. So it is a solution. Okay. Any questions? I know it probably sounds very elementary, but it's going to get more difficult soon. Well, not today, but it will. Yep.
Do you prefer that for stuff like this that we show doing everything else and then simplification, or do we jump straight to simplifying stuff? So like you do the replacing things, would you want us to show all the work out of the replace? Yeah.
Yeah, I personally would prefer to see at least this line. You can skip this line if you want. You might even skip this line, because I imagine that by the time you get to this line, like look at it, like, oh, 15 minus 18 plus 3 less than 0. Yeah. You definitely don't have to show all the work I did, but it's I would say maybe the substitution part. Definitely keep it. It's easy to grade if you have that. And even work on the side, I think it's helpful to taking the derivative. Good point. All right. Any questions? All right. The next example is, so we're going to verify that x equals c1 e to the negative t plus c2 e to the 2t is a solution to the differential equation x double prime minus x prime minus 2x equals 0. So in this case, it's different from the x before. The previous example, the x is the independent variable, right? Y depends on x. But here, x is actually the dependent variable. It depends on t, which is the independent variable. You can also tell by just looking at the derivative. So this is dx, d something, dt. And also we want to find solution to the equation that satisfy initial conditions in the future, I'll probably just write ICS, means initial conditions. It just means that condition when t equals 0, when the time equals 0. So the initial conditions are given in this example. It's given x of 0 equals 10, x prime of 0 equals 0. So two parts. One is that we want to know if that's the solution to this equation. The second one is that we want to find a solution to this equation that satisfies the initial condition. They kind of follow from each other. So let's do the first part. Just like we did before, right? We need to find the x prime, find the double prime, put in there. So if we have left side equals the right side. Questions? So x prime, so based from this given solution, so let's find the x prime. Taking the derivative, c1 stays, e to the negative t derivative is e to the negative t, but then the exponent negative t will give you a negative using chain rule there. And then plus c2, and the e to the 2t is e to the 2t, but then the 2t will give you a 2, so 2c2. The second derivative, again, we just take the derivative of this existing one. So this part stays, and then you're going to have a negative from here coming to the front. Here you have 2c2, but then you're going to have another 2 coming from the exponent. So I'm going to do it quick here. So that just becomes positive c1 e to the negative t plus 4c2 e to the 2t. Is that okay? It's just like a negative times negative is positive c1. Now I'm going to put in there into the differential equation. So that will become c1 e to the negative t plus 4c2 e to the 2t. This is the second derivative part. Minus the first derivative, negative c1 e to the negative t plus 2c2 e to the 2t. That's the middle term. And the minus 2x, which is minus 2 times c1 e to the negative t plus c2 e to the 2t. This is the last term. It should equal to 0. At this point, we found the derivative, we plug them into the equation, we just have to simplify, right? So I would say probably get rid of all the parentheses, distribute the negative, and then distribute the negative too. Let's see what we get. So that will be c1 e to the minus t plus 4c2 e to the 2t minus a positive c1 e to the negative t minus positive 2, so that's a negative 2c2 e to the 2t. Distribute the negative 2, so that's a minus 2c1 e to the minus t minus 2c2 e to the 2t. Is that equal to 0? To be honest, I'm being a little bit lazy, so I kind of don't want to write down the fractal form. So I kind of just look at it. So looking at the e to the negative t term, so I have c1 here. Then I have another positive c1, so that's positive 2c1. But then I minus 2c1, so the e to the negative t term, right? So let me box those. So I have c1 and then another positive c1 e to the negative t, then minus 2c1 e to the negative t. So if you kind of combine those terms, you get a 0, right? And the e to the 2t term, you get 4c2, then you get minus 2c2, minus another 2c2. Again, that kind of goes away. Give you 0. If you want an extra step, it's good. You can just write down 1 plus 1 minus 2 c1 e to the minus t plus 4 minus 2 minus 2 c2 e to the 2t equals 0. You get 0 equals 0. You don't have to do the work if you look at it and then you know what the sum is. Questions? All right. So it is a solution. So we know what the solution is. Let me just copy it down. You don't have to write it down. Which is x of t equals c1 e to the negative t plus c2 e to the 2t. So that's given. But we want this solution, not just this solution. This is the general solution. Because there could be many different ways to write it, depends on C and the C1 and C2. We want to know the specific solution that satisfies the given initial condition. So we want that solution to satisfy those two conditions. Basically, we need to find out what C1 and C2 are. So need to know this number and this number. We're just going to take the initial condition and plug into this solution. So use the initial condition, x of 0 equals 10. So we're just going to take this, x equals 10, t equals 0, right? t equals 0, x equals 10, put in there. So we get 10 equals whatever the rest is. So we get 10 equals c1 e to the negative 0 plus c2 e to the 2 times 0. Let's plug in t equals 0 for all the t, and plug in 10 for all the x, which is 1 on the left. Questions? And then we can simplify, because e to the negative 0 is e to the 0, right, which is 1. And the e to the 2 times 0 is also 1. So we just have 10 equals c1 plus c2. That's fine. No, we can't really solve, but that's okay. Then we have the other initial condition, which is x prime of 0 equals 0 is the second condition given. Now this one tells that this tells us that when t equals 0, in the derivative of x, we get 0. We have to use the derivative of x, which is this one. This is the one that we're going to use for the second condition. So let's plug in t equals 0 again, and x prime equals 0. So we get 0 equals c1. Nope, I get negative c1 e to the negative 0 plus 2c2 e to the 2 times 0. And if we simplify, that's a 1. This is also 1. So we end up with 0 equals negative c1 plus 2c2. Oh, sorry. You realize that it's a bit too low. Does that kind of make sense? So you have to pick the correct equation to solving the initial condition. Now it's really just solving this. If you solve those two equations with the coefficients, I'm not going to go into the details solving them. I hope that's okay. So we just end up with, if we add them, so the C1 will cancel, we get C2. 3C2 equals 10, C2 equals 10 over 3. And the C1 will become 20 over 3 if you solve it correctly. I hope that's okay. Not showing the word. And now we have C1, C2. We know what the solution is, satisfying the initial condition. So we get x of t, just rewriting this, is equal to C1, which is 20 over 3, e to the minus t, plus C2, 10 over 3, e to the 2t. This is the specific solution. I'm not sure. I think they might call it particular solution, but I don't remember. Any questions on those? There are two steps. One is to show the solution is the actual solution satisfying the equation. The second part is to use the initial condition to figure out what the constants are. Any questions? All right, if you don't have questions, I'm going to move on to the next part, which is I'm going to write down in the book there was 4 common equations, differential equations, and the solution are given. So the first one, so this is the common differential equations. The first one is dy dx equals ky. And the solution has the form y of x is equal to c, some constant c, e to the kx. Sorry. So if you have some differential equation, right, dy dx equals, for example, 5y, and then the solution will look like this, except for that's a 5. If you have k equals 10, you always have this. So this is what we call the population growth model, or because if you think about y, dy dx, y is the population, x is time, so dy dx is how much does the population change, the rate of change of the population for 1 year. And if this is a positive number, it depends on, for example, that's 1% of the current population. So the population increased by 1% of the current population, then you can end up having a exponential growth population. The second one is basically the same. It's just that you have a negative. And the only difference is that we have a negative sign in the exponent. It's an exponential decay model. The third one is that if you have a second derivative of y with respect to x equals negative k squared y. And the solution is slightly different, which will be y of x equals C1 cosine kx plus C2 sine kx. And the fourth one is similar to number 3, but again the solution will be different, with a positive on the right hand side, not a negative. And the solution will be C1 e to the kx plus C2 e to the minus kx. So those are the full basic differential equations that we already know what the solution will look like. So that if you given a problem like this, you might just see a different constant on the right-hand side. That's it. But the overall form is the same. So the solution, the form of the solution doesn't change, but what's changing is the constant in exponent. You don't have to memorize this, but it's kind of good to know them. I'm not saying you have to memorize it, but it definitely saves a lot of time if you know what the solution looks like. At some point, we're going to actually derive the solution by following a process. But for now, we just take those for granted. So here's the example. So solve the equation. Differential equation d squared x dt squared equals negative 9x. Find solution satisfying the initial condition x of 0 equals 1, x prime of 0 equals 0. So this is the differential equation, and we need to know what the solution is. And the solution has to satisfy, well, not only this equation, right, but it also has to satisfy those two initial conditions. And we haven't talked about how to find it yet, right, because this is a second order homogeneous linear ODE. We haven't talked about how to solve that yet. Eventually we will. But for now, how do we figure out the solution? For today, to find the solution, we're just going to take this and look at the full common one that I wrote earlier. Which one does it look like this one? Number 3, right? Because we need a second order. So 3 and 4 are second order ODEs. And then we need a negative value on the right hand side, so that's going to be number 3. So this one I'm giving you looks similar to d squared y dx squared equals negative k squared y. Basically the same, right? The difference is that the 9 corresponding to k squared, that tells us that k equals 3. And the x corresponding to the y, the t corresponding to the x, if you try to match the variables under the constant k. Well, why do we do this? Well, we do this because for this differential equation, we already know what the answer is. We know that this one has the answer, I'm just going to copy it down, y of x equals c1 cosine kx plus c2 sine kx. So that's the answer to this known equation. So if I match the variables correctly, that means for this one, I can actually write down the answer in this form. So the answer to that differential equation, by following the existing differential equation, it just instead of y of x, so the y here is what this x, the x here is what that t is, right? So that would be x of t. And the C1 is just C1, cosine is cosine. K, we talked about k squared is 9, so k equals 3. Take k to be positive. And the x is t, and then C2 sine 3t. By following this answer, we can write down the actual answer for the given problem. You're not going to do a lot of this, just for this type of questions. We have to do it this way. So that's a solution. It's a general solution. We need to make sure that it satisfies, this solution satisfies the initial conditions. So plug in x of 0 equals 1. So put in there, so I got 1 equals C1 cosine 3 times 0 plus C2 sine 3 times 0. Right? Plug in this 0 is the t value, the 1 is the x. If we put in there, and if we simplify correctly, the sine of 0 is 0, the cosine of 0 is 1, so we just have 1 equals C1 times 1 for now. Is that okay? All right. The next step is we need to plug in the x prime of 0 equals 0, but we don't have x prime yet. We have to find it. So find x prime of t first before we can plug in. So just take the derivative. That's going to be C1 cosine is negative sine, so negative sine 3t. 3t will give me a 3 in the differentiation process, plus C2 sine will give me cosine, 3t will give me a 3. So that's the derivative from the general equation. Now we can actually plug in the second initial condition. X prime of 0 equals 0. So we get t equals 0, the first derivative becomes 0, so that's a 0, 0. So we get 0 equals negative 3c1 sine of 0 plus 3c2 cosine of 0. Again, just simplify, that's a 1, this is a 0. You just end up with 0 equals 3c2. Which tell you that C2 has to be 0. So we found C1, we found C2, and I'm almost done. So now we can actually write down the specific solution, satisfy the initial conditions. So that's x of t equals C1, which is 1. I don't even have to write the 1, cosine 3t, plus C2, which is 0. 0 times whatever is 0. So that's this is the specific solution. This is a general one. Any questions on that? So that's, I guess my point with this problem is that sometimes they ask you to solve the equation, we just haven't have the tools yet. So what we do is we kind of match it with something we know. Like if it's the correct type of, if it's the same type of differential equation, we're just going to kind of match the answers. Questions? No? All right, one last comment. In the textbook, I really recommend that you're reading it. It's a very straightforward reading. It's not like a regular textbook. It's more like a lecture notes. So if you go to the textbook and then look at the section 0.2, try to read it through. I don't think it's taking very long. At the end of that section of 0.2, 0.2.5, you get a lot of exercise. I think a lot of questions are very good. We did something like the first couple, and then we look at something like this. That's what this example is. It's good to try some on your own, so that way you'll be prepared. Any questions? Yeah. Yeah, there'll be, the professor probably going to either type them out or see, oh, do those problems from the textbook. I'm not sure exactly where the problem will come from, but it will be something that you just kind of write it on your notebook and then submit it somehow. Good question. Any other questions? All right, take care, and I'll see you on Tuesday. And stay warm, enjoy the snow.